Okay, some interesting takeaways that we should make about the differences between lenses and mirrors. Uh, if you wanted to label them by their shape, we can. A concave mirror has its own shape, but there are other ways that you can label a mirror. Depending on how old you are, you might hear them said different ways. The concave, we could label it by its shape. We could label it by its function. The concave mirror is converging. Or we could label it by its focal point. You might also hear this called a positive mirror. So this will be by its F. The other one for the mirror is convex, or it's diverging, or it's a negative mirror. So let's keep the function the same and see what happens to the lenses. If I have a converging lens, there's a lot of different shapes that we can use, but typically this would be the double convex. And that's weird because the shape is opposite for the same function. And part of that has to deal with, are we reflecting or are we transmitting? All right, so that's that. And then this is something that is common to it. What about its focal point? Well, we found that this was a positive lens. And if we had come into the studio, they're actually in little wrappers from 30 or 40 years ago, and they say positive lens with the focal point. Okay, if we wanted the diverging one, this would be where the shape flips again. Double concave. It's still diverging and it's still negative. So some key differences between mirrors and lenses. The shapes of these functions flip when we go from one to the next type. Okay, how about some other observations? The converging lenses or mirrors, they can give you two options. They can produce real images if the object is outside the focus. And we saw that in both ray diagrams for the converging. The other species it can make are virtual, and they are always magnified. Okay, so we get bigger ones. These are converging devices, are magnifying mirrors or magnifying lenses. Diverging is always virtual, and they're always demagnified. And I can't make another type of situation like with the converging. If we were inside the focal point, then it changes the way these things interact, and it causes always divergent rays. If you're on the outside, then it always causes the rays to converge, right? So that's the difference. Like right when you're at F equals, or at object equals F, that's when an inversion happens, when you go from real into virtual. Diverging, there's only one way to draw this picture, right? The focal point's over here. I can be really close to it and get these kind of diverging rays, or I can be really far away from it, but does it really make a difference? No, it's the same picture, right? This is exactly the same picture as that one, just this distance is different. So anyway, from 0 all the way out to infinity, you're always going to have the same type of ray diagram. Therefore, you're always going to have the same results. Virtual, always demagnified. Okay, just another observation that we should make about lenses and mirrors. If you have a single device, what are some things that we noticed about them? In all the cases where we had real images, they're always upside down. Okay, the magnification I can't say anything about, but I can say that they are always upside down. If you had virtual images, either from concave or convex, They're always going to be upright. What about in cases where you have multiple devices? These rules don't apply. And we've got an example coming up where there's two lenses in a row, right? And the first one creates something upside down, but then that upside down goes through the second lens. So if you have multiple devices, it's possible to get two inversions of this type, or it's possible to get one and not one, or whatever. So if you have two devices that are doing this in a series, these rules don't always apply, right? Because you can get two or fewer. But if it's just a single one by itself, you can rest assured. Real images are always inverted from a single interaction, and virtual is always upright from a single interaction. Here's a special case of the mirror that I guess I didn't really cover before. What happens if we have a plane mirror? What is the radius of curvature for a flat surface? We talked about this before when we proved that the Earth is in fact flat, right? If the radius is really large, then it looks flatter and flatter at the surface. So let's say the radius is infinity. And the focal point, of course, is infinity over 2, which is still infinity. Okay, and is it plus or minus? Well, it kind of doesn't really matter. So in that situation, what do we have? Say 1 over f equals 1 over I plus 1 over p. If this is infinity, then what's that mean for the, no, that's not infinity. Ridiculous. Focus is infinity, so 1 over I equals 1 over p. Well, we can see from here that goes to 0. So 1 over p is equal to negative 1 over I. The image distance is negative the object distance. And this is like a bathroom mirror. If you're over here, then your image will be back here. Same distance away, but inside the mirror. How about the magnification? Are you magnified in a mirror? Negative I over p. Well, we just said that I was equal to negative p, so equals negative p over p plus p over p. Your image in the bathroom mirror is a virtual, upright, non-magnified in any way image. And it is exactly as far back as you are in front of the mirror. So it's just kind of a special case. What other observations can we make about mirrors, or lenses for that matter, dealing with issues like infinity? Okay, so an interesting new situation would be, what happens if we put the object at the focal point? And this can be for a mirror or a lens, but I'll just use a mirror here as an example. So this is F, I've got my focal point, or my object right on top of it. This can be a little bit crazy to deal with, right? So what are the options for the ray diagram? I need to connect the tip of this to the mirror. So come in flat, and then reflect through the focal point, right? So that would be something like this. And this goes way out here to somewhere, right? It's just an intersection. The other one is I need to aim for the focal point and then bounce off the mirror. So I start at the tip and I want to aim for the focal point, and then boom. This goes all the way out to infinity at some point. And in theory, I guess, at some point it had to have hit this, right? Infinitely far away, and then bounce back flat. So here we are at infinity. This ray is coming back flat. Flat. So I do get an intersection of this ray somewhere far, far out here at infinity. And what can we see from the ray diagram? It's really hard to say anything. It looks like this, again, is infinitely far away, so this will never stop. It'll continue to go on infinitely. The image appears to be positive infinity, and I say positive because it's on this side. What can we say about the magnification? It's very, very large, right? So it's maybe infinitely magnified. Minus infinity will give us something like that. It's just a huge, infinitely large inverted image. Okay, fine. What about the proof for that? If 1 over f is 1 over p plus 1 over I, and we said that p is equal to f, so I guess I'll call that f, these two terms cancel. I get 0 equals 1 over I. And I is, in fact, infinity with a plus sign in front of it. So that's interesting. What can we say about that? The magnification is thus negative I over P, which is minus infinity over something that's not infinity. Here we are, minus infinity. So what's the take home about that? Well, if I wanted to put an image, let's say not an infinity, but really far away, right? I wanted to make a projection of an object really far out there. I'd want to take that object and try to put it at the focal point, because doing that would give us as large of an image as possible and is projected on a faraway screen. Now, obviously, you can't get it exactly at the focal point, right? Because our objects are three-dimensional, so not all of it will end up going to infinity, but just parts of it will go to infinity. And overall, most of the object will be in the range really close to the focal point, so we'll get numbers that are very large, but not necessarily infinity, except for one, minute portion of the object. We can flip this on its head too and kind of do some stuff that physicists typically do. What if I had a really far away object? So I want to say my object is at infinity. We'll see if I can get this diagram to work out correctly. And maybe for funsies, we'll use the lens this time. All right, so let's make a couple of focuses. This one's gonna be fake. And my object is way the way out here at infinity. So where would its rays come in? The first one would need to transmit through F. And the other one is kind of complicated, right? Because I want this to end up coming through the middle, right? So I want something that looks like that. But the problem is, this is so far away, this angle is going to be flatter and flatter and flatter as this gets further out. And we can see that here. If it was here, then my angle would be, hell, let's just try it. All right, so if my object is here, here's the angle, and as it gets further away, what are we noticing about that line? It gets flatter and flatter and flatter. So let's assume this goes all the way out to infinity. As far out as I can pull this, what's my ray look like? It looks like that. It's on the axis. So for the smallest ray or smallest angle possible, this would end up coming through like this. And where is my image? I is here. Not at P. At the focal point. This is a really great way to measure the focal points of unknown lenses, and you'll see physicists do it all the time. We're like crows. When we walk past the makeup aisle or the bathroom aisle or anywhere that's got magnifying lenses, we can't resist it. We have to pick it up, use a light from the ceiling, and then project some kind of an image onto our hand just to eyeball and estimate what was the focal point of this device. It never fails. So that's something that we might do. We can say, well, the image is approximately at the focal point if P is really far away, right? And of course, the ceiling lights aren't infinitely far away. So we know there's a little bit of error, but this is going to be pretty close. And that's the point. If we wanted to prove it, you can do the same thing with the sun. We were just talking about burning ants with a magnifying glass. You've got an image of the sun 93 million miles away. That's pretty close to infinity, but not exactly. And the image that you put on the paper isn't exactly a point. It is a small disk, so the magnification doesn't go down to exactly 0. Okay, so we'll just try it. 1 over, we said F, is 1 over P plus 1 over I. If this is infinity, then this whole thing goes to 0. And there you go, it's right there. 1 over F is 1 over I, or I is equal to F. And the magnification, if that's minus I over P, where this is, I guess, minus F over, who cares, because P was infinity. You should get a negative 0 magnification. And that might sound insane. Well, what's negative 0 mean? I'm just indicating that it would be upside down if we could get an image that was resolvable. So that, I think, is most of what we have to talk about.